Okay, hi everybody. My name is Ali Shirsavar. I'm delighted to be here today, in particular because this is the first time that I've had to wear a shirt since last March. I haven't been allowed out of the house for a year now, so it's good to be able to present to some people. Today we're going to talk about PCB layout fundamentals. There are a great deal of guidelines and so on the internet about PCB layout, but it is very difficult to apply these beyond the circuit that they're describing in an application note if you don't follow the actual fundamentals. And today we're just going to talk about how to deal with fast changing current, mainly because we've only got 15 minutes. Okay, so a quick introduction. There are many tips and guidelines and so on for correct PCB layout on the internet. The problem is that often these guidelines conflict with each other and they can be sometimes even contradictory. Many times the guidelines are either vague or ambiguous. Exactly how many millimeters is as close as possible to avoid jitter. Exactly how far away is as far as possible to avoid crosstalk. If you have to avoid jitter and crosstalk, what is as close as possible and as far as possible at the same time. I'm going to talk about currents in particular today, in particular the ones in power supplies. And many times you read that we have to minimize all the loop areas. I mean, and how can we do that at the same time? You cannot have zero space if you minimize absolutely everything. It's not physically possible. Now, none of these guidelines are incorrect. In fact, all of them are correct. It's just that we need to decide when to give priority to each guideline, which one is the more important one at the point of the layout that we are going to be laying out. Now, thankfully, often all we need is to apply some high school physics. So we just need to know some high school physics fundamentals, which we've all studied at school, but it's just that we haven't applied it to PCB layout. So in this webinar, we will first talk about some fundamentals that you need to correctly route fast changing current traces. By that, I mean current traces that have got very high DI, DT, the rate of change of current. Then after we talk about this high school physics stuff, then we apply these fundamentals to a real life circuit and remove some of the ambiguity surrounding the PCB layout so that we see, okay, which one of these loops I minimize. I cannot minimize all of them. Which one is the one that is going to give me the biggest headache? And I'm going to prioritize that one in order to, in order to get a better PCB layout. So first, a quick reminder of high school physics. Rule 1, right-hand screw rule. You would have done this at the school at some point. And it basically says when a current flows in a conductor or a cable or a PCB track, a magnetic field is formed around it. It becomes magnetic. We will represent this with what we call magnetic field lines. The right-hand screw rule allows us to determine the direction of these field lines. Now, the direction of these field lines is important because depending on how you lay out your PCB, you can either lay it out in a way that these magnetic field lines cancel each other, or they reinforce each other. For example, if you want to build an inductor, you want these magnetic field lines to reinforce each other. If you want to have a quiet PCB track, we usually would like these magnetic field lines to cancel each other. And we'll talk about this a little bit later. If you hold your current carrying conductor, this is the right-hand screw, with your right hand, and with your thumb pointing at the direction of the current, then the way your fingers curl is the direction of the magnetic field lines. And remember, we want to know the direction of magnetic field lines because later on we will see how we can cancel the magnetic fields with these. Okay, so that's the direction. There we go. That's the direction of the current. My thumb is pointing at the direction of the current. Then the magnetic field lines will go the way my fingers curl, provided that I hold it with my right hand. Right, so, and the magnetic field lines is going that way. That is something that we studied at physics in school, and we will see shortly how this helps help us in laying out a PCB. Now, let us look at the conductor from the top. So if you imagine this was my conductor, I was holding it like this. It's a lot easier if I look at it like this. So what I'm going to do is I'm going to rotate the conductor and look at it from the top. Now, the current coming towards us, again, if you remember from the school day physics, if it's coming towards you or out of the page, right, then we represent this with a dot. And of course, what I said was, it's coming towards us. The thumb is pointing at the direction of the current, which is coming towards us. My fingers are curling this way, and therefore the magnetic field lines go this way. On the other hand, if I hold the thing in the opposite direction, my hand is like so. We represent that with a cross, like an arrow that is going away from you, and you just see the feathers at the back of the arrow. That's the cross. The arrow coming towards you is the pointy bit coming towards you. Again, the fingers show the direction of the magnetic field lines, and you get these two. Okay, so we've done all of this before. How does it relate to a PCB layout? In the world of theoretical physics, we can have infinitely long current carrying wires. We can be suspended in vacuum. They can be 1 meter apart from each other, and a current can flow in them forever to infinity. Now, in real life, unfortunately, that cannot happen. In real life, current comes out of a battery or a source and must return to it. Otherwise, it won't flow. Therefore, currents always must flow in a loop. So we have a conductor that goes out this way and comes back. We have got a loop. Otherwise, the current will not flow. So by using the right-hand screw rule, we can decide how to route each path of this loop to either increase the magnetic field or cancel it. Okay? Using the right-hand screw rule, we will see shortly that the smaller the loop area, the smaller the magnetic field emanating from it. And of course, if you have ever been to an EMC test chamber, you know how important this is. This is why PCB layout tips often say minimize the loop area. Obviously, though, we cannot minimize the loop areas of all the tracks on our PCB, and therefore we have to be selective and we have to find a compromise, right? We also need a few other simple rules that I'm going to talk about shortly, after which you can have an intelligent selection criteria as to which loop is the most important that I need to minimize and give priority to it. So, how the magnetic fields affect our PCB. This is a PCB that I've got from the top view, and this is its side view. So I've made a crappy one here. So this is one from a top view, and this one here is when I'm looking at it from this way. It is often easier to look at the PCB this way in order to see what the magnetic fields are doing. Okay, so we can see the magnetic field lines much better from the side view as opposed to the top view. So what happens? You've got a current that, let's say, is going from here back down to here in a loop, right? Here's my right hand. The current is going away from me, so I need a cross. The magnetic field lines look like so, and here is my right hand. The current now is coming towards me, so I represent it with a dot. The magnetic field lines go this way, right? And let's expand the number of magnetic fields. There we go. The total magnetic field would look like so. Now have a look at the direction of the magnetic field line here, 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 and here. It's there, 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 and there. And you can see that these are actually in the same direction, which means that inside of the loop, not only these two don't cancel, inside of the loop, they add to each other, okay? So inside of the loop area, the magnetic field lines due to the forward and the return current, so due to this one and this one, actually reinforce each other, right? And therefore, we will get, oh, can I move this without messing things up? No, I can't see the top of my own screen. Magnetic field lines, oh, thank you. Magnetic field lines of the left conductor plus the right conductor. In this region, they add to each other. But they're quite far from each other. So outside of this loop area, so in this area and this area, the magnetic field of this conductor does not have any impact on this one, and vice versa. The magnetic fields of this conductor outside of the loop, so in this area and this area, does not have any effect on this one. Okay? So, therefore, you can see that in this area and this area, you see the magnetic field of only this conductor. So here you see the magnetic field of this one. Here you see the magnetic field of this one. This is similar to an inductor with a single turn, if you ignore this resistance, right? And of course, we know that the inductance of an inductor is proportional to the area, okay? Now, let us consider another case whereby it's exactly the same circuit, but instead of having it like so, I've made it like so. So I have minimized the area inside of the two conductors. So that is the forward path, that is the return path. Again, I'm going to look at it from this angle because it makes my life easier. I can see it better. Now, this is still just another inductor with a single turn, but you can see that the loop area now is much, much smaller, and therefore its inductance is smaller. Okay, let us consider now the same current going through the loop with a much smaller area. So again, that is my right hand. The current is going in that way. This is my left hand. The current is coming back towards me. In the center, they reinforce each other, just like the previous example. But now look at what happens outside of the loop area. Okay, inside the magnetic field is exactly the same, right? There we go. But now the area is much smaller. So the inductance is smaller. But outside is the important bit. Outside of the loop, if you apply the right-hand screw rule, you'll see that now this one is going in the opposite direction of this one, and therefore they actually cancel each other. So you get a double whammy here. Not only you minimize the loop area, and therefore the amount of inductance is smaller, the amount of magnetic fields spewing all over your circuit in the test chamber is smaller. Outside of the loop area, provided that the forward current is the mirror of the return current, which often, but not always it is, right? They actually cancel each other. So you end up with no or little or no magnetic field on these areas. And suddenly, this area of your PCB is quiet. Whilst in the previous example, this area of the PCB had the magnetic field due to this line here, and this area of the PCB had the magnetic field lines to this conductor here. Okay, note that the cancellation is just an added bonus. If the current is not an exact mirror, you may not get perfect cancellation. Okay, so now what is the best way of minimizing the loop area and canceling stuff? One of the most effective way of minimizing is to route the return current right on top of the input current. So as the current goes in, the return path comes under, as I've shown. This is my PCB. This is the current going in. That is the current coming out. There we go. That's the current going in. That's the current coming out. Now this, if you have two layers, has got the advantage that is usually the smallest area that we can achieve, right? You get a much better area if you put these two together. Then often all the magnetic field is contained within the body of the PCB, right here, right? So that is where the magnetic field is, there and there, okay? As an added bonus, if the current is exactly the same, but in the mirrored, so this one is the forward current and that is the return current, then everywhere else, just like we saw in the previous slide, actually the magnetic fields cancel. So you end up with no magnetic field outside of these two tracks. And of course, that means that it's quiet from an EMC perspective. Okay, so if our return current is going to ground and we have a ground plane or on an adjacent layer, right, then the current will actually automatically return under here, right? We'll talk about this a little bit later. So if you actually poured copper right under here, and that's your entire ground plane, you don't even have to route it. It will naturally, because of laws of physics, which we're going to talk about a little bit more, that's a school level physics, it will naturally flow right under the current that is going in. Okay, so let us have a look at that. Return current on a ground plane. Here I have got a PCB. This is the top layer, right? And let's say that the return from here is going to ground, and this is the bottom layer, and this is the copper pole of the ground layer, okay? I am going to show the current on the top layer with dashed black lines, and I'm going to show the current on the bottom layer with solid red lines. Okay, so this bit here is connected to ground, and of course the bottom layer is the copper pole, right? Now, for a DC current will take the path of least resistance. Okay, so current on the top layer going from there to there, that is from there to there, and then through there to there, and then it's going to return, right? And that's current on the bottom layer with the red line. The total area is this much, right? And it's DC, which we're going to give it low priority. We are not too much worried about DC with a big loop area. I'll explain that why in a minute. Now, high frequency current. So if your current is changing, right, then it doesn't follow the path of least resistance. It follows the path of least inductance. And of course, the path of least inductance naturally, because of Faraday's law and Lenz's law, is right under the current that is going up. So this is again the current on the top layer going from there to there. But if it's high frequency, instead of taking a B line, a straight line over there, it will naturally flow from there to there and there to there, because that is the path of least inductance. That's why we twist two conductors together from the current going in and returning. Okay, and the area is naturally minimized, and of course around it the fields are cancelled. Okay, now which magnetic field on our PCB do we care about? Now, if you remember from the previous slide, I said that with DC we give it lower priority to high frequency AC. Now consider that we've got a magnet and we've got a coil or a PCB track. Obviously, we cannot minimize all of the tracks, so we're going to have to be selective. Now, if I rotate this magnet, I will get a changing or time-varying magnetic field. We know from school-level physics that Faraday's law says that we have an EMF, which is a voltage induced in the coil or our PCB track. The faster we spin the magnet, the bigger the induced EMF. And if we stop moving the magnet, we get zero EMF because no magnetic field lines are being cut. There is no di dt. Well, in case of Faraday, it would be d phi dt because it's talking about flux, but flux is proportional to the current. And a changing magnetic field in the middle of your PCB from an EMC perspective is a nightmare. According to the Lenz's law, the direction of the induced EMF will change depending on whether it's the north pole of the magnet that is cutting the line or it's the south pole, and it opposes the movement that is causing it. So you end up with a rotating magnetic field. If I physically get a magnetic field, a permanent magnet, start spinning it on a bunch of conductors, I will induce an EMF, which will be a sinusoid. Okay? But we don't have to have a permanent magnet attached to a drill spinning in order to have a changing magnetic field. As soon as we change any current on a PCB track, we get a changing magnetic field. And that is why an AC current changing is a lot more important in terms of EMC and PCB layout than DC, because an AC current is like a rotating magnetic field. It's a time-varying magnetic field, whilst DC current is a magnetic field that is constant. Let us look at our PCB one more time. A DC current will form a magnetic field like so. So the current is going in this way, is coming back the other way. This is the magnetic field lines according to the right-hand rule that we discussed. This looks like a permanent magnet. Now, we know that it's not time-changing because it's DC, and we know from school-level physics, if you remember, magnetic field lines come out of which pole and goes back into which pole? Florian, you're the only one who can talk. Doesn't matter, right? The magnetic field lines come out of the North Pole. I see. The magnetic field lines come out of the North Pole and return into the South Pole. So the North Pole of the magnet is here. Magnetic field lines come out of it and they go into the South Pole. The South Pole is there. Having a DC current is not usually a big problem because it will not directly induce an EMF in other PCB tracks. The magnetic field is not changing and not time varying. Okay, but AC or otherwise time varying currents will act like a rotating or a moving magnetic field from the previous slide. Faraday states that the induced EMF is proportional to the rate of change of current. Therefore, it will induce unwanted voltages in PCB traces nearby, including itself, including its own track. And the rate of change of current, the higher the rate of change of current, the more of a nightmare this thing is going to be. Okay, so the conclusion is that magnetic fields line due to time-varying currents, which should usually be given more priority for loop minimization compared to DC. So we are immediately seeing, if you've got many loops, which ones you should select first on your PCB layout to minimize. Then let's look at another thing. Time-varying current in a track would be similar to a rotating magnet or a moving magnet interacting with a PCB track. There we go. You see here, right, that an AC current will be doing this, right? A DC current would be only going in one direction. AC is going moving back and forth, back and forth, back and forth, right? And therefore, you end up with a magnetic field that looks like this. Yeah? It's not dissimilar to that rotating magnetic field. You've got a changing magnetic field right in the center of your PCB. And if this magnetic field interacts with any other tracks, you're going to induce an EMF. According to Faraday's law, we would induce unwanted voltages. We would induce them in the tracks nearby via something called a mutual inductance, how much inductance there is between this track and tracks around it. And we would induce a voltage in this conductor itself via its self-inductance, because it's one loop of wire and it's got some self-inductance. When considering the effect of the changing magnetic field to a changing current, we know that the induced EMF is defined as minus L di dt. We have seen this many times before, right? The inductance times the rate of change of current. And we know when you consider tracks away from the magnetic field but being impacted by it, the induced EMF is E minus M di by dt, where M is the mutual inductance and L is the self-inductance, okay? Di by dt is the rate of change of current, which means the faster you change the current, the worse it will get, just like a switch in a power supply. So let's have a look at the self-inductance first. Example 1. Let's say we have a current that changes direction at a rate of 100 kilohertz, and that current will induce a bigger voltage in its own conductor compared to the same current with the same magnitude rise and fall times, right, of a 1 kilohertz AC current, right? Now, therefore, as the frequency goes up, things get worse. But more importantly is actually the switching transition, how fast you switch things on and off. The faster you switch things on, the IDT gets worse. So you again have got something to select. You look at which current is changing faster. Now consider we've got a MOSFET with let's say we've got a switching frequency of 100 kilohertz, right? Let us assume that the turn off and on time for the MOSFET is 30 nanoseconds. And let's say that it goes from 0 to maximum of 6 amps. Just for simplicity, let's work out how much is going back and forth here, right, at the rate of 100 kilohertz, rise and fall times of 30 nanoseconds and going from 0 to 6 amp, right? So if it goes from 0 to 6 amps in 30 nanoseconds, the IDT, the rate of change of current, is 6 divided by 30 nanoseconds, which is 200 mega amps per second. Okay? Now, let us assume that our current carrying track is 5 centimeters long and 1 millimeter wide, again, just for simplicity, right? And a rule of thumb for a lone 1 millimeter wide, the standard FR4 PCB track is that every centimeter has got around 8 nanohenries of inductance or 20 nanohenries per inch. Therefore, the induced voltage spark in its track itself that is changing is 5 centimeters times 8 nanohenries times 200 mega amps per second, and that's 8 volts. You get an 8 volt spike, right? For minimization of loop priority, I would say this one's got a high priority because you're getting 8 volt spikes if you don't minimize things. Okay, now let us assume the same loop, but this time let's just consider not the track itself, but another track cutting the magnetic field lines of this particular current changing, right? And we call this magnetic coupling. Let's say I've got another track on a different layer that looks like this. Is cutting this high di by dt trace. Again, the current is going back and forth. The magnetic field line is moving. It's just like a rotating magnet, right? And it's going to cut this line here, and therefore it's going to induce an EMF with transformer action, if you will, in the other conductor. So let us also assume that this thing is going to a reset pin or a clock pin of a sensitive IC. For simplicity, let us assume that the mutual inductance between the signal track and the switching track of the MOSFET is 5 nanohenries. Using exactly the same numbers, the magnitude of the induced EMF on this track that is just crossing a different layer on here is going to be around 1 volt. And that is, let's say, going to the clock or to a reset pin, right? Our power supply was switching at 100 kilohertz, so this spike may appear at every switching transition, which is at a rate of 200 kilohertz on a clock pin. And that's why it's important that if you have got a loop that has got high di/dt, you minimize this and you actually try to cancel. In addition to minimizing track length and loop area of high di/dts, we need to keep sensitive tracks away from these places, these areas of high di/dt, high change of magnetic field. So this was the fundamentals that we talked about. Now let's apply this to a real life example, let's say like a buck converter. Clearly, the traces will have high and fast changing currents are the ones that we have to prioritize. Switching power supplies are usually the worst offenders for these things because you have got big currents changing all the time. And there's high di/dt, right? But even within the switching power supply, you still have to be selective because you never have enough space on your PCB. So out of these areas and loops and branches, which ones I should give priority to minimizing? If we consider a buck converter, let us consider and grade the loops in order of badness. Which loop is the worst? Okay, there are loops that only deliver DC. For example, the output from here on, it's only DC. Okay, there are loops that have very fast switching currents, right? And those are the ones with the switch and the diode, the switching elements. Here and here, they are turning on and off in orders of tens of nanoseconds. So these will have high di/dt. And then there are loops that have ripple current, right? So they still have some changing magnetic field. They have di/dt, but it's not as bad as these switching ones. And this is the ripple current through the inductor and ripple current through the capacitor. I will show you the waveforms in a moment. So we have to choose which one's worse. Here we go. In the switch on period, so when this switch is on, SW on period, then the diode is off and the current flow looks like this. So the current goes from there to there. This is on, that is off. When it gets to this point here, it splits. The DC current goes down here, the AC current goes down here. So it splits and goes like so. And then here it rejoins and then it returns. Okay, that's during the switch on period. During the switch off period or D on period, when the diode is on, the switch is off, right? So there's no current flowing that way. And then the current looks like that. The current goes from there to there. Then again, it splits just like so from here to here. Then it rejoins and it goes there. So we've got one loop that goes this way. We've got another loop that goes this way. We've got one loop that goes this way, down through the cap, and another loop that goes here, down through the resistor. Okay, please don't be scared of these waveforms and then how you work them out in real life. You literally just simulate it and you will see exactly where the currents are, and then you see where there is high di/dt. Now I've done this for the buck converter and you'll see what's going to happen. Now let us look at the currents on each branch during the switch on period and the diode on period. So during the switch on, for now we're just going to look at the current going in, right? And then on the next slide, we look at the current returning. So this is the switch on period. sorry, this is the switch current as a whole. Switch on period, you can see fast rise time, current ramping up, and then you turn it off. Switch off period, there's obviously no current, and then it repeats. That's off period. Then this is the diode. During the diode on period, you see that the current is freewheeling through the diode and is ramping down. And during the off period, obviously, there is no current in the diode because the switch is on. Okay? And what really happens is that you are switching on, off, on, off in an interlaced way. So it's going to look like that. Yeah? When the switch is on, the diode is off. When the diode is on, the switch is off. And these two add together at this junction and go through the inductor. So the inductor current will look like this. You can immediately see that these one and this one have got higher di dt. This one has got a ripple current, right? But not as high a di by dt. Then what happens is that the DC current goes through your load. That is DC, so it's got no di dt. And then you've got your capacitor, which is the remainder of this inductor current. So this is the capacitor ripple current. Okay? Then we looked at the current going in. Let us now look at the current coming back. The switch current looked like that. The diode current looked like that. The inductor current looked like that. DC current from the resistor looked like that. And the ripple current from the capacitor looked like that. Now these two add together, so you end up with a current here in this branch here, which is the exact mirror of the inductor current there. Again, please don't be scared of how you work these out. You simulate them and you put a current probe and you can see which tracks, which loops are important for you to minimize when you do your PCB. Then finally, the return current has to be what's going in, has to come back, and it looks like this. And again, that is a mirror of that. And remember we said if you've got a mirror current, provided that we route these on top of each other or we stick them on a ground plane, if it's a ground current, then they naturally flow under each other and cancel each other out. So you've got inductor current there, you've got the mirror of the inductor current there, you've got switch current there, you've got the mirror of the switch current here, you've got diode current here, but you don't have a mirror. So this is the one that you can't properly cancel. Okay, how do we choose which loops? We can see from the previous slide that the branches with the switch and the diode have the highest di dt. The branches with the inductor and capacitor have ripple, but not as much di dt. And the branches with the resistor is DC and therefore no di dt. We should really also talk about dV dt on the switch node, but unfortunately in this short webinar, we don't have time to do that. Note that the current through the switch is mirrored exactly at the bottom, right? So if we route the two under, we can get some cancellation. And note that the trace current in the diode has high di dt, but does not have a mirror current under it. There we go, that's a diode current. Okay, so in order of priority, minimizing loop, I would give this one top priority. I would also give you either first equal or second top priority. So these two are absolutely essential for minimizing. Okay, how will we lay it out? Now that we know which loops are bad, this is really bad, this is really, really bad, this is really bad, right? It's almost always a bad idea to lay out anything just as you see it on the schematic. So if that is your schematic, please, please, please don't lay it out like so, because they will have a massive loop here, that is the switch and the diode, and you have another massive loop here, that's a diode and the inductor, and this will cause you pain. Okay? We need to think carefully about positioning the components, rotating them around, and see what we can do in order to minimize the critical routes. Okay, if you route exactly the same thing, these are exactly the same components, but what I've done is I've wrapped it like a U shape here, right? This was actually, I read a beautiful book by Sanjay Maniktala, which actually talks a lot of good things about how to lay out power supplies, and he recommends this method. There we go. Now that loop is minimized, and that loop is also minimized. In this particular case, if we wrap our components so that our input connector is near our output connector, then we minimize our critical loop areas. Okay, this is for a single layer board, but we often have a minimum of 2 layers. In this case, we can then use the other layer, the bottom layer, to copper pour the ground net and create a ground plane. Okay. Sadly, we don't have time to discuss ground planes, power grounds, signal grounds in great detail. We also didn't have time to discuss switching node and DV/DT, but there is a lot here already that can help, hopefully help you in routing your power supply better. The high frequency current, you must remember, follows the path of least inductance, but not the least resistance. The path of least inductance is where the magnetic field of the return current naturally cancels the magnetic field of the forward current, right? In other words, we do not need to route the return current under the switch, for example, if we have poured a copper and if there is no cut on the ground plane. If you remember, there is also many guidelines about never put a cut in the ground plane, never put a cut in the ground plane. Actually, sometimes you don't have a choice. You have to put a cut in the ground plane. It's just that you shouldn't put it under the path of high DI/DT. If you put a cut, if you put a cut in the ground plane somewhere where the current is DC, then it's not too big a deal. If you put a cut in the ground plane somewhere that you have massive switching current, then it is a big deal. So again, you can be selective, but unfortunately, we don't have time to talk about that anymore. Okay, finally, the control circuitry can be added away from the noisy traces. You're going to have to shift and move your components in such a way that you can put the control traces away from noisy noisy part of your circuit, right? But we don't have time to discuss these in detail, but all the fundamental laws that we discussed can be applied in exactly the same manner, right? The signal with the highest DI/DT in an IC is the gate drive signal. So the gate drive signal has to push a lot of current very fast into the gate of the switch. So that is the one that you need to minimize this loop, okay? So it will look something like this. You've got here, again, the input connector. You've got the output connector. This part here is the ground. That is your MOSFET. That is your diode. I've wrapped them all out in order to minimize the loop. Let's say that this is the control IC, and let's say that is the gate drive to the top switch, okay? Remember that this is floating, the top switch. It's not, there is no ground, right? The return current is not the ground, but there is a return. So what you have to do is make sure these are as close as each other, right? Now, if there is no high frequency current going around this way, you could route this under and put a cut in your ground plane. But you have to be careful and you have to make sure that it does not interfere with anything. But well, look at what I've done here. I know that I've got high DI/DT on the gate drive, and therefore I have minimized this loop. Oops, I haven't minimized the other loops, right? Few other things whilst we are on the subject. On a voltage mode control, the most sensitive signal that is far away from the control IC and needs to be returned back is actually the voltage feedback potential divider signal, right? So that has to traverse through these places, and it's very sensitive because that's your feedback signal. So as I said in the previous slide, you need to keep these sensitive signals away from the noisy bits, okay? And you have to route them away. You minimize the loops. You make sure that you cancel everything. You take then the output voltage and you try to get it to your control signal as cleanly as you can. You have got to have usually you have to have a voltage potential divider. Don't put the potential divider here on the output voltage, because then you increase its impedance on the track and you make it easier or more susceptible to pick up noise. Put the potential divider right next to the IC. And that way, you've got low impedance going there, so it's less susceptible to noise. You route it as best as you can, and you bring it over here. In terms of a current mode, the most sensitive signal is the current sense resistor, the current sense signal, which comes from the current sense resistor. You put that again not far away, as close as you can to the current sense pin of the IC, with many wires to the ground plane. And the second most important is the voltage feedback, which you also apply the same principles. Okay, and that is how you lay it out. Underneath the board, if you put a island of ground on the bottom layer, right, and only connect at one point, that is where the signal current connects, signal ground connects to the power ground. Okay, now on a voltage mode where signal ground connects to power ground is by the potential divider, so close to here you connect the two ground layers together, and on a current mode the signal ground connects to the power ground near the current sense resistor. Okay, so concluding remarks. I hope you enjoyed the presentation. Unfortunately, we didn't have much time to go through anything else apart from the loops. We hope to resume our in-person workshops in Germany and in the US starting October 2021, COVID permitting, obviously. We offer our usual analog PSU design, digital PSU design, and EMC filter design. Then we are working on a distance learning PCB routing for EMC compliance workshop. And that will have by far more details than what we discussed today. And there will be videos that you can watch offline. There will be a step-by-step simulations in order to show the basic principles, which you can do, again, yourself at your own time. There'll be a step-by-step hands-on experiments that you can do on your own. What we're going to do is we're going to send you the EVMs that you need with very detailed guidance or laboratory scripts that you follow, and then there will be answers to, or there will be there'll be videos to show you how the experiments should have been done, and then there may be some live presentation and questions and answers for more complicated materials, or if anybody has any questions. This is what we're hoping to be. We are preparing right now. We're amidst of it. Please register on www.biricha.com/Omicron in order to download this current presentation and be kept informed of what we're going to be presenting in terms of workshops and webinars and so on. This is the end of the presentation. I hope you enjoyed it, and thank you very much for listening.